In this section, we are going to look at several different chemical bonding theories that explain things that Lewis dot structures do not explain. So in preparation for those theories, we are going to be looking at a Lewis dot structure and then counting the groups of electrons around the central atom. So groups of electrons doesn't sound technical enough, so to say an electron domain, that sounds a little more techy. And then I abbreviate that as EDs, and the electron domains on the central atom include lone pairs, that will be one domain, and bonds. So a single bond is one electron domain, a double bond is also one electron domain, as is a triple bond. So if I start out with, the reason we're going to count electron domains, by the way, is the number of groups around the central atom are going to dictate the geometry around that central atom. So since electrons repel each other, they will automatically maximize the angle between them or get as far apart from each other as they can. So I'm going to look at the case where we have two electron domains around a central atom. So for example, hydrogen cyanide, we have drawn this before in class. And if we did the dot structure for this, we would end up with 4 lines, and our triple bond has to go to nitrogen because hydrogen can only have 2 electrons around it. So that would be the correct dot structure. So all of our focus is going to be on the central atom. So carbon has 1 single bond around it and 1 triple bond around it. Each atom in this case has a formal charge of 0 because it's got the number of valence electrons around it that it likes to. So we discussed that earlier. The point here is there are two electron domains, and several textbooks treat the electron domains like balloons. So if we tied 2 balloons together, we would get this linear position. So 2 groups of electrons, they're going to repel each other, and the maximum angle between that would be 180 degrees. So 2 electron domains translates into a linear electron domain geometry. So that's another big long word I'm going to abbreviate. So if we are taking a look at just the electrons, that would be the electron domain geometry. So linear automatically has 180 degrees associated with that. So this would also be the case for carbon dioxide. And in this case, all we care about is the central atom. So it's not essential that we have all the dots on all of the outer atoms. But in this case, carbon, the central atom, also has 2 electron domains around it. This could also be true for a diatomic molecule, for example, carbon monoxide, Carbon triple bonded to an oxygen. And in this case, neither of these atoms would have a formal charge of 0. But if we treated this carbon as the central atom, the lone pair is one group, and the bonding electrons are another group. So in each one of these cases, the carbon has 2 electron domains around it. So the electron domain geometry, again, is the shape of the electrons. That's not necessarily the shape of the molecule itself. So this may not have been in an introductory chemistry course. We're going to just process through. So 2 electron domains is automatically electron domain geometry would be linear. So again, I call this EDG, the electron domain geometry. If we have 3 groups of electrons around a central atom. We've drawn several structures like that. And so the first one I'm going to draw is SO2. So if we do a quick dot structure of SO2, the divide by 8 method works beautifully as long as we don't have hydrogen. So the available electrons here, 3 electrons, and 3 atoms, each has 6, that's 18 electrons. We divide by 8, so that gives us 2 bonds and 2 remainder. So that we can tell right away that sulfur is going to have 2 dots on it from that remainder right there. And then we still have to know that the 2 bonds don't necessarily mean 2 single bonds. So if I draw the O's here, I would still select one position to put that double bond. SO2 would have 2 resonance structures because of the choice on where to put that double bond. More importantly, it's got 3 electron domains. So that is 1, that is 1, and that is 1. So each group of electrons, whether it's a lone pair or a bond, counts as 1 electron domain. And so here we would say this is 3 EDs. And if we tied 3 balloons together, we would get a shape called trigonal. Well, basically we get a perfect triangle. But we say trigonal planar electron domain geometry. So 3 groups of electrons, because they are going to repel each other, are going to take this position. Approximately 120 degree angles between them. So that is, I'm just going to put approximately 120 degrees. Lone pairs actually take up more room than bonding pairs. So these angles here would be a little bit greater than 120 degrees, but that's not the focus on what we're discussing here. We're just looking at these basic electron domain geometries. So 3 groups of electrons around a central atom are going to take this trigonal planar position. We have also drawn SO3. And so when we drew sulfur trioxide, we ended up with 3 resonance structures where the double bond alternated. This structure also has 3 electron domains. Okay, so this would also be trigonal planar electron domain geometry. The molecular geometry is a little bit different, and that's not really the focus here, but I'll go ahead and state that. The molecular geometry is the atoms only. So when we do X-ray crystallography on a sample, the electrons don't show up. So the shape of the molecule itself, you may remember this from another class, this would be bent. So the molecular geometry here is bent on the SO2. For SO3, we have the trigonal planar electron domain geometry as well. Trigonal planar electron domain geometry and the molecular geometry, so I call that MG. So molecular geometry. The molecular geometry is also trigonal planar because there are no lone pairs. So again, the shape of the molecule itself is not critical here. We're learning the electron domain geometries. So every theory that we're going to look at in this next unit is going to depend on how many groups of electrons there are around the central atom. So a valid dot structure is essential for coming up with the correct dot structure. So we could have 3 electron domains. If one of the electron domains is a lone pair, then the electron domain geometry will be different than the actual molecular geometry. So again, this one also has 3 electron domains. This one would have exactly 120-degree angles between each sulfur-oxygen bond. So since this is an identical environment, then these angles would be exactly 120. If our molecule is distorted by either having a different atom or lone pairs, then these angles may not be exactly 120. But what I like my class to know is that a trigonal planar electron domain geometry translates into 120 degrees between groups of electrons. For electron domains, there's a variety of different molecules that would fit that. So all of these, I'm going to have 4 electron domains. That becomes tetrahedral electron domain geometry. So if we tied 4 balloons together, we would get this tetrahedron, and your textbook probably has a much better picture of it. It's kind of hard for me to draw that. But a tetrahedron's got 4 vertices to it. If we glued 4 equilateral triangles together, we would get a tetrahedron shape. So the angles here are 109.5 degrees. And that would be the case if we had identical atoms or identical things, which they'd have to be atoms, no lone pairs around the central atom. So if I draw methane, CH4, this has 4 electron domains, 1, 2, 3, 4. And here the Lewis dot structure makes it look like the angle between electrons is 90. But if we turn this 2-dimensional representation into a 3-dimensional picture and tied 4 balloons together, all 4 of those hydrogens would be here at the 4 vertices of this tetrahedron. So this is tetrahedral. The Mg, the molecular geometry, is also tetrahedral, and that's because there are no lone pairs. And remember, our X-ray crystallography does not pick up electrons. So when we take a picture of any molecule, the atoms are what deflect those X-rays. So 4 electron domains translates into tetrahedral electron domain geometry with 109.5 degrees between those angles. We could also have NH3, ammonia is the simplest amine group, nitrogen group. So if we draw NH3, there are also 4 electron domains, 1, 2, 3, 4. So the electron domain geometry is still tetrahedral. So anything with 4 electron domains is going to have a tetrahedral electron domain geometry. But the molecular geometry here, if we remember, we call this trigonal pyramidal because we end up getting like a small pyramid. And I don't make my class memorize all the molecular shapes. Whether or not we have lone pairs is going to dictate the actual shape of where those individual atoms are. So again, this is the molecular geometry that we're looking at here. But 4 electron domains is still tetrahedral. Electron domain geometry. So these angles would be a little bit greater than 109.5 because those lone pairs take up so much more room that they repel these bonding electrons away a little bit. There's another very common structure that's got 4 electron domains, and that would be water. So if we draw water's dot structure, it might look linear the way we draw the Lewis structure, But this also has 1, 2, 3, 4 electron domains. So this has got a tetrahedral electron domain geometry. And you may remember the molecular geometry of this molecule is bent. So the MG, or the molecular geometry, when we look at atoms only, is bent. So if we were to try to draw water so that it looked three-dimensional, we might put the lone pairs on the page and then try to show with a perspective drawing like a wedge. So this hydrogen is supposed to be coming out toward us. And then we would try to draw a hydrogen going behind the paper, but we really don't need to do all that for this class. What we need to be able to do is just do the dot structure correctly, make sure the central atom is correctly represented, and then count groups of electrons. And the molecular geometry, often referred to as just the shape of the molecule, won't be the same as the electron domain geometry if there are lone pairs on the central atom. So if all of the electron groups have atoms there, then the electron domain geometry and the molecular shape will be the same. For an expanded octet, any atom that lives on the third row of the periodic table so that's anything that lives in the n equals 3 row of the periodic table. Since we're looking at molecules, which are nonmetals, as long as we're on the third row, phosphorus, sulfur, chlorine, any of these guys can have more than 8 electrons around them. We might see some structures that have xenon as the central atom. So even though xenon already has 8 electrons around it, because of the d orbitals available to anything on the third row, we'll see some compounds that have xenon as the central atom. So an expanded octet, remember when n equals 3, we have a 3s orbital, one of those, and then there's always the p orbitals occur in 3s, so here's where our magic number 8 comes from. But then there are also d orbitals available. So an expanded octet is going to use up to 6 orbitals. So that would mean that we're going to use 2 of those d orbitals. So an expanded octet is possible for n equals 3 or greater atoms. Okay. So if we have 5 groups of electrons around a central atom, that would be 5 electron domains. 5. So 5 electron domains, and if I look at PCl5, for example, phosphorus is under nitrogen, so it's got 5 electrons around it. Each chlorine, there's 5 chlorines, each chlorine has 7 electrons around it. So this gives us a total electron count of 40 electrons. If we do the quick divide by 8, this gives us 5 bonds, and more importantly, the remainder is 0. So we know that the central atom is not going to have a lone pair on it. So we put phosphorus in the middle and 5 chlorines around each phosphorus, well, around the phosphorus. And I don't really need to put all the lone pairs on the outer atoms, but we can see here that there are 5 groups of electrons around phosphorus. So if we tried to tie 5 balloons together, we're not going to get a nice flower picture. What we end up getting is a perfect triangle, but this triangle should be perpendicular to the paper. So we have a trigonal base, and then one balloon directly above and one balloon directly below that triangle. So we would call this trigonal bipyramidal, and textbooks generally have much nicer three-dimensional drawings of that. So here is where our phosphorus would be, and a chlorine in the horizontal triangle, and then one chlorine directly above and one chlorine directly below that triangle. So 5 electron domains translates into a trigonal bipyramidal electron domain geometry, and the angles here are 120s, and the angle here would be 90. And this is one of the few cases where the positions of the lone pairs would vary. So we call this triangle, we call this the equatorial position. So if we think about it like the Earth's equator, so this is the horizontal plane, that's where the triangle is. And that's where the 120-degree angles are, around that triangular equatorial position. The axial position, if we think about an axis, or the axis on the Earth, the axial positions are at 90 degrees, or they're perpendicular to this horizontal plane. So this is the vertical position, and that's where the 90s are. So our next structure, we're going to have one lone pair on the central atom. So that lone pair will always occupy this position where there's a 120-degree separation. Anyway, it is possible to have 5 groups of electrons around a central atom. So the Mg for this, since all 5 of those electron domains have atoms associated with them, the molecular geometry is also trigonal bipyramidal. I'm not going to do every possible structure here, but I am going to give us one more example of 5 electron domains. Okay, so let's start this up. If we have sulfur tetrafluoride, SF4, we might be tempted to just connect 4 fluorides to the sulfur with single bonds, but we want to make sure we do that electron count. So sulfur's in group 6. Each fluorine is in group 7. And again, I'm using the available electrons only now. But sulfur has 6 valence electrons around it, and fluorine has 7. So if we add up all those electrons, 28, 29, 30, this is 34 electrons. So I like the divide by 8 method whenever we don't have hydrogen. If I divide by 8, I get 4 bonds, but the important part of dividing by 8 is the remainder. So the remainder of 2 electrons is going to show up on our sulfur. So if I put sulfur here, I put that remainder on first, then I connect all 4 atoms, all 4 fluorines to the sulfur. And if we did the quick dots around everything and counted, we would see that this structure, as long as we put all the lone pairs on each fluorine, this structure will have 34 electrons. So this also has 5 electron domains. And the lone pairs would actually show up at this equatorial position. So here we'd have sulfur and a fluorine in these axial positions, and then one fluorine to this vertice and another fluorine to this vertice. So the shapes start getting very unusual for the molecules. This one ends up being the molecular geometry we call seesaw, which doesn't sound very technical. It looks to me like a teeter-totter. So if we built the molecule, I don't even know how to spell teeter-totter. I'll try it, I guess. So if we built this with balls and sticks, we would not put the electrons on here. This thing would kind of wobble back and forth. 6 electron domains is the maximum number we can have. So I'm going to do that on the back side. So if we have 6 groups of electrons around the central atom, 6 electron domains automatically translates into an octahedral geometry. Octahedral electron domain geometry. And an octahedron is what we would get if we glued 8 equilateral triangles together. We'd have 8 faces on that shape, but only 6 vertices. So I can't really draw one of those very well. My best shot is just drawing a square. So this would be perpendicular to the paper, and then an atom directly above, or an electron group directly above and directly below. So if I was a good artist, I could actually draw the octahedron, and we would see that there are 6 vertices, a vertice on each corner of this square, and then one above and one below. So we could call this square bipyramidal, and it would be similar to the 5 electron domains. But we don't say square bipyramidal because we end up getting an octahedron, a nice geometrical shape. Okay, and I can't think of one right offhand that has all 6 atoms. Maybe this one. Let me try SF6. I'm pretty sure this will work. So sulfur hexafluoride, if we do an electron count, sulfur is in group 6. And then each fluorine, 6 fluorines are in group 7. 42, yeah, good. So this gives us 48 electrons. If we divide by 8, we get 6 bonds and a remainder of 0. So if we connect sulfur, again, the dot structure, this might just look like a flower. So there's nothing really wrong with the dot structure not being a great representation of the molecule. The main purpose for the dot structure is to get the environment of the central atom. So since we know there's a remainder of 0 and there's 6 bonds, we can count 1, 2, 3, 4, 5, 6 groups of electrons. And an octahedral geometry, everything's a 90. So that's a 90-degree angle on the square, and then a 90-degree angle here where we have the horizontal plane and the vertical plane. So 6 groups of electrons around the central atom means that we're going to have an octahedral electron domain geometry. If the molecule has 6 atoms around the central atom, then the molecular geometry is also octahedral. There's a square planar complex that's pretty common. So I'm going to go ahead and give us that one. If we had PTCl4, and this doesn't seem like it should be a molecule because platinum is a metal, and this non-metal, it seems like this should be ionic. But there's another type of compound that we'll discuss in later chapters, a metal complex. But if we treat platinum as though it has 8 valence electrons, so it's got d electrons, that makes it a little confusing. And then plus 4 times 7, each chlorine is in group 7, we get 36 electrons, 36 available electrons. If we divide by 8, we get 4 bonds and a remainder of 4 electrons. So in that case, we know that the platinum is going to have 2 pairs of electrons around it, as well as the chlorines. So if we put platinum here, put a chlorine and a chlorine, we want to make sure that we show the lone pairs. Don't try to put them in between the atom and the lines, but distinctly draw those lone pairs so that when we count groups of electrons, we'll see 1, 2, 3, 4, 5, 6. So this again is octahedral electron domain geometry. And if we were to draw this structure in 3 dimensions, we would see that the electrons, the lone pairs of electrons, get as far apart from each other as they can, because lone pairs take up a lot more room than bonding pairs. So in this case, the electrons, the lone pairs, really are exactly above and below that central atom. Then our chlorines would actually point to the corners of this square. And then when we take a picture of just the molecule, all we see are the atoms. So the lone pairs that are directly above and below this square horizontal plane don't show up on that picture. So the molecular geometry here is square planar. So this molecule really is a perfect square. I haven't discussed whether things are polar or non-polar on here. It gets a little tricky with the larger atoms, but here this would be non-polar. So that may make some of you say, no, it's not. It's got lone pairs on the central atom, but in this case, the lone pairs really are exactly above and exactly below that platinum. So this is a non-polar molecule because it's very symmetrical. Okay.